This matrix maps the complete diagnostic framework for open channel flow. AEE exam success depends on locating a fluid's position in space and time. Every condition is dictated by two parameters: depth change over space, dy over dx, and over time, dy over dt. This 3D cutaway of a channel flow system shows how these different mathematical states exist simultaneously. At different points in the same channel, a stable, uniform flow can transition into a gradually varied profile before hitting a terminal hydraulic jump. The dimensional complexity arc breaks the engineering math into 4 progressive stages, starting with the uniform baseline and moving through spatial variation, rapid disruption, and finally temporal disruption. This space-state progression serves as the diagnostic framework for the entire engineering discipline. Correctly identifying where a physical flow phenomenon sits on this theoretical arc is the only way to apply the correct engineering boundary conditions. The absolute baseline for flow is the steady, uniform state. Here, both dy over dx and dy over dt are 0, meaning depth is constant across both space and time. In this state, the engineering objective is optimization. We need to maximize discharge while reducing the frictional resistance caused by the channel walls. To minimize friction for a given excavation area, the wetted perimeter, the total length of the channel boundary in contact with the fluid, must be minimized. Refining a standard trapezoid to reduce that boundary contact leads to the most efficient profile possible, the half hexagon. In AEE exam problems, the half hexagon requires specific mathematical constraints. The side slope angle must be exactly 60 degrees, and the side slope length must equal the bottom width. Under these precise conditions, the hydraulic radius, r, will equal exactly half the flow depth. This idealized geometric baseline defines the hydraulic constants that all subsequent spatial or temporal equations must reference to describe the flow. When we introduce spatial variation, dy over dx is no longer 0. The depth changes slowly over long distances, while the pressure distribution remains hydrostatic. This comparison highlights the core diagnostic question: is the bed slope, S0, greater than or less than the critical slope, SC? That relationship dictates whether the natural normal flow, YN, sits above or below the critical depth, YC, establishing subcritical or supercritical conditions. The GVF profile matrix categorizes surface behavior into 3 depth zones. These zones are determined by the specific energy curve of the system. A universal rule applies here. Surface profiles rise in zones 1 and 3 and drop in zone 2. Horizontal and adverse slopes present a mathematical anomaly. Because normal flow cannot exist on these slopes, zone 1 profiles are physically impossible to generate. Mapping these GVF profiles allows engineers to predict the exact upstream distance before backwater overtops a dam or floods a channel. Beyond categorizing the curve type, engineers must calculate the physical distance, delta x, over which the profile extends. The selection of a methodology depends on whether the channel boundaries are man-made or natural. The direct step method uses specific energy comparisons, but is only valid for prismatic, geometrically uniform channels. In natural rivers with uneven topography, engineers must use the numerical integration method, which integrates the dynamic equation of GVF despite the high computational cost. Applying a prismatic calculation method to a natural riverbed results in significant errors when identifying flood zones. Rapid spatial disruption occurs when the fast-moving flow abruptly shifts from supercritical to subcritical, forming a massive hydraulic jump. To calculate the mechanics of the jump, we assume the pressure distribution is strictly hydrostatic and ignore losses from boundary friction along the floor. As the alert bar indicates, the massive loss of kinetic energy is caused by internal eddy formation and extreme turbulence. The Bellinger equation mathematically locks the downstream depth, Y2, to the upstream conditions and the Froude number. This formula box shows how to calculate the pure head loss, delta E, caused by this turbulent transition. The Froude classification gauge shows how the jump's destructive potential scales directly with the upstream Froude number. Engineers target the steady jump range between Froude numbers 4.5 and 9.0 when designing stilling basins for energy dissipation. Forcing a hydraulic jump through design provides a highly controlled mechanism for energy dissipation, protecting downstream structures from high-velocity kinetic erosion. In the final state, unsteady RVF, flow properties change rapidly across space, while simultaneously and continuously changing over time. These states are typically triggered by sudden mechanical operations, such as gate closures or turbine load rejections. The resulting surge wave acts as a moving boundary, forming an interface between two different steady flow states. This flowchart tracks the reaction of the fluid system to these sudden operations. A sudden gate closure generates a positive surge backing up upstream, and a negative surge starving the downstream flow. Conversely, a sudden gate opening causes water to rush out, creating a negative surge upstream and a positive surge pushing downstream. Accounting for these mechanical time variations necessitates the shift from steady-state formulas to unsteady kinematic equations to solve for the moving wavefront. Bringing this analysis back to the central matrix, we see how every flow condition is a subset of these four quadrants. The engineering workflow begins by optimizing baseline geometry for discharge and then tracking gradual energy changes over distance. The second half of the workflow accounts for violent energy dissipation and the mechanical shocks introduced by temporal changes. Open channel flow is a deterministic system, manageable once the parameters of space and time are quantified.
How do engineers design massive water infrastructure to move the maximum amount of water while keeping construction costs as low as possible? And how do they manage the violent energy of water when the terrain suddenly drops? Welcome back. Today, we are mastering channel efficiency and varied flow behavior, two heavily tested topics you need to secure high-yield marks on the APPSC AEE exam. Let's quickly reset our baseline. You already know the continuity equation. Discharge equals the cross-sectional area, A, multiplied by velocity, V. We measure the cross-sectional area of the water and trace the wetted perimeter, P, along the boundary where water touches the channel walls. Now we introduce the most important variable, hydraulic radius, or R. This is simply the cross-sectional area divided by the wetted perimeter. This ratio represents the exact balance between the volume of water you are trying to move and the surface area of the walls causing friction against it. Because it defines that physical relationship, it is the ultimate metric for measuring channel efficiency. To calculate velocity in uniform flow, we rely on Chezy's equation and Manning's equation. Look closely at the variable S. This is a common exam trap. S does not stand for the physical bed slope. It specifically represents the energy slope, or SF. However, in a strictly uniform flow, the water depth remains completely constant. Because the depth doesn't change, the water surface and the energy line run perfectly parallel to the channel bed. So for uniform flow, and only uniform flow, the bed slope mathematically equals the energy slope. Now let's look at economical sections. If your goal is to push the maximum discharge through a fixed cross-sectional area, the math tells us you have to maximize the hydraulic radius. Since hydraulic radius is area divided by perimeter, maximizing it means you must make the denominator, the wetted perimeter, as small as physically possible. When engineers design a trapezoidal channel, they take the derivative of the perimeter with respect to depth and set it to 0 to find that exact minimum value. This math dictates strict geometric rules. For an economical rectangular channel, the ideal bottom width is exactly twice the depth. For a trapezoid, the most economical shape is exactly half of a regular hexagon, built with 60-degree side slopes. Let's test this right now. If you are designing an economical rectangular channel with a flow depth of 4 meters, what is your required bottom width and hydraulic radius? The bottom width must be twice the depth, so 8 meters, and the hydraulic radius is half the depth, giving us exactly 2 meters. Minimizing the wetted perimeter has a dual benefit. It maximizes hydraulic efficiency by reducing friction, and it directly reduces the surface area that needs to be lined with expensive concrete, saving massive construction costs. We've looked at uniform flow. Now let's analyze the total energy in the system. Specific energy is the total energy of the flow measured strictly relative to the channel bed itself, ignoring any outside elevation. This curve plots the specific energy depth relationship. For a single specific energy value, there are 2 alternate depths, a deep subcritical, Y1, and a shallow supercritical, Y2. At the nose of the curve, they merge into the critical state, hitting absolute minimum specific energy.
At this critical state, the Froude number is exactly 1. For a rectangular channel, you calculate this critical depth by taking the cube root of the specific discharge squared divided by gravity. This frequently comes up on the AEE exam as a direct ratio. For a rectangular channel, the specific energy at critical depth is exactly 1.5 times the critical depth itself. Identifying this critical depth is an essential diagnostic tool. It allows engineers to predict exactly whether a channel will flow smoothly or if it is on the verge of a volatile state change. When conditions change, the flow stops being uniform. If the water depth changes infinitesimally slowly over a long distance, we call it gradually varied flow. Because the acceleration is virtually zero, the pressure distribution remains comfortably hydrostatic. But if the channel bed abruptly drops or an obstacle appears, you get rapidly varied flow. The water depth shifts suddenly and violently. The ultimate example of rapidly varied flow is the hydraulic jump. This occurs strictly when a fast-moving, supercritical flow crashes into a slow-moving, subcritical flow. Engineers deliberately force these turbulent hydraulic jumps. When water leaves a dam spillway with massive kinetic energy, forcing a jump dissipates that energy before it can scour the riverbed and destroy downstream infrastructure. Let's tie this all together with a capstone question you might see on the APPSC AEE. Imagine an economical rectangular channel with a Froude number of less than 1. If the flow depth is slightly increased, what happens to the specific energy? A Froude number under 1 means slow, subcritical flow. This places our state on the specific energy curve's upper limb. Since the curve slopes outward here, any increase in depth pulls the point right on the x-axis, increasing total specific energy. This 4-quadrant cheat sheet summarizes everything we've covered: Chezy and Manning formulas, economical section rules, critical flow equations, and the mechanics of a hydraulic jump. Understanding how these formulas relate allows you to navigate the most complex multi-step problems on the AEE exam with precision. Keep practicing, and you'll see exactly how predictable these problems become.